All right, everybody, welcome to our last Saturday morning science of the spring semester. I'm already working on the fall semester, but if you have any suggestions, feel free to email me and let me know. So we've got a really special Saturday morning science this morning. We have 5 speakers who are all experts in different areas of computer science, informatics, and AI. And I'm not going to introduce all of them. I think Chi-Ren is going to do that. So I will just ask everyone to please silence your phones. And I don't know what we can do about our phones hearing us while we talk about them, but maybe they'll give us some information on that too.
Okay, good morning. So, I'm sure everybody's interested in AI, right? Good or evil, or so that would be a fun discussion today about AI. And my name is Chi-Ren Shyu. I'm director of Informatics Institute and also professor from Electrical Engineering and Computer Science Department. I will introduce our panelists later in this talk here. It's my great pleasure to also invite our dear colleagues from different areas, to have open discussions with the audience about AI. I'm sure, you experience AI in your daily life, right? What do you think about AI? What type of AI technology you experienced in the past 24 hours? Your car. Your car, a fancy one, Mercedes? No? Change lane, yeah, spot here. Yeah, my car is too old to have that. So, yeah. So you have this kind of, stuff here. Anyone use Alexa? No? No one use Alexa? No? Use Alexa? Okay. So you ever heard the news about Alexa? They might have someone over, try to hear your stuff. Then Amazon hires thousands of employees to hear your stuff and try to label things. That's exactly what, the precursor of some AI stuff. Okay. Um, so let's look at. Let me do that here. Let's look at some technology here. How many of you? How many of you were at the driverless car before? Anyone? Anyone took that? When I was in San Francisco, I took that. And at the beginning, I was like, is that going to... And busy traffic, really. Busy traffic was pedestrian here and there, just perfectly. I was not involved in any accident. I'm here, right? So, so this is really a technology really using AI to do that. And how about this video here? Have you seen this video? It's called Deepfake. Deepfake is, you can download the software from GitHub to pull out the deepfake. It's like you can train my face, and then you can put my face over Jennifer Lawrence's face, and then to see not my voice, like Jennifer's voice, right? And then my face on the video for that here. So I don't know why people develop this one here, but that's a really bad idea, right? If you think about fake news, that's part of this kind of technology might cause some issue here. IBM Watson, you heard about Watson all the time, right? Use weather channels powered by IBM Watson, right? Watson is great. Watson is great in many areas here, including higher education, retention, and also recruitment here. Jeopardy, right? Jeopardy 2011. Jeopardy, I remember we were here with a watch party with IBM folks from St. Louis, from the headquarters, and we sit there to look at the Jeopardy, right? About that episode for that. How about healthcare? Anyone heard about good thing about IBM Watson for healthcare? Okay. Anyone heard about bad thing about that, or something not really successful about that? Okay. MD Anderson pulled IBM Watson out of their diagnostics for oncology for that. Okay, they spent millions of dollars. Oncology figured out the solutions may not be ideal for their practice for that. Okay, so what does that mean here? That means AI is here but still not there yet, right? Okay, Amazon, right? This Alexa here. I don't know. I turn it on once and then I turn it off. I I'm a geek, right? But I still don't feel comfortable someone really listen over my conversation. One time my daughter was in a house, like a friend's house. They talk about buying some certain clothes things, those kind of stuff here. And then after that conversation, like the friend went to Amazon website and then pull out all those type of the products like related to their conversation. Okay, pretty cool, right? And sometimes like that may not be the best thing like you experience in your life. AlphaGo, okay? And then how about medical robot? Do you expect like in the future someone look at your chest X-ray and say, look, that is good. This is like has some cancer here. It's already happening, right? FDA already approved some of the products for that here. So I'm sure like Dr. Sheets is going to talk a little bit more about that. And then how about 737 Max? Okay. Autopilot has been here for a while, right? Autopilot really try to mimic how human, like how pilots try to work on that, so captain can go back to sleep, and then just like if that's the intercontinental flight, that could be 13 hours, right? So pretty good idea, but in many cases, like we got to look at how human can gain the control back for that. Okay, so just like some of the idea here. So artificial intelligence in like language definition. Okay, they talk about is all your computer science geeks like work here, right? A branch, not bunch, a branch of computer science dealing with simulation of intelligent behavior in computer. Okay, so I don't really know what's the definitions this one here. So this is from like Association of Computing Machinery. That's the major society in computer science. They talk about, if you read this one here, talk about environment, you talk about take actions, maximize the chance of successfully achieving its goal here, right? So you got to look at, just like human, right? You got sensors, you got your eyes, we call that computer vision, you got your ears, we call that like could be natural language processing, speech processing, right? You got smell. We don't have much about smell, right, in computer science for that. You got touch. You got the feeling about that here. So you got sensors, you got environment, and how you use that to mimic human cognitive function and with human mind. Okay, so are we there yet, right? If you talk about like later, like our colleagues here are going to talk about more advanced machine learning and how that is going to solve many real world problems here. But is that still here yet? Like really to replace human, or like to mimic how human works for that? Okay, and then try to learn and problem solving. So that's the definition of that. Of course, you talk to 10 different like computer scientists, they'll give you more than 11, right? Definitions of what's AI here. Okay, so don't take my word like my definition. I use this like information. So here's a history of AI. So let me use 12 words to talk about history, right? Do you like me to be your history teacher? Like 12 words talk about entire AI history. Wow, exciting, sad, exciting, sad, exciting, and more exciting. Okay, so that's exactly like the cycle of AI in the past for that here. Okay, so you do get like 1642 here, really like French mathematician Pascal really put together like some mathematical formula, like mathematical like work, and also like mechanical calculation about like behavior, human behavior. So let's skip all the way to Alan Turing. Okay, have you watched the movie called The Imitation Game? Right, Alan Turing. So for those of you who are not computer scientists folks here, uh, the Nobel Prize in computer science is called Turing Award. That's the top honor of a computer scientist. Each year they give to one or two like computer scientists. This year they give to two, right? Was the someone doing deep learning. So we're going to talk more about deep learning here. So all the way, like you talk about like 1965, and then 1980s. That's when I touched AI when I was in college, and then you can look at that from 1997. That's Deep Blue. Try to compete with the chess master for that. You know how big is that machine? It's not this machine here. I went to IBM Watson, in New York, state of New York here is that a huge machine. Like that machine can really hit the entire building during the winter for that. Okay, so that's the deep learning, deep blue here, and you can see like it's a long period of time. We call that AI winter. AI winter, right? A lot of hypes, a lot of excitement, and then boom, we overcommitted. We overpromised too many things for that here. So that's the period of time, if you publish a paper in AI area, they will warn you, don't do that because you won't get a job. And I experienced that. I had a paper at Triple AI, and then colleagues came to me and said, look, don't publish more, okay? Because AI is really bad for that. That was back in 90s. So you can look at that here all the way to 2011, the Jeopardy game for that. And then before that, 2002, you guys were like an iRobot, right? I remember you use iRobot at home. I have iRobot. That's the best $250 I spent. Like get all the I got a terrier at home, so it's pretty much good. It's great. Still working at this point here. And then you look at let's look at 2016. This is AlphaGo. AlphaGo really is a breakthrough. It's like they don't need to have a lot of training set. They said no training set, right? They just quickly learn from the behavior, and then they just beat the master for that. And then we have more and more computing power because of the big data, because of the infrastructure is growing like this way here. We can always go back to those mathematical work. We cannot make it happen because we couldn't make it happen because it's too expensive to compute. Now because of the computing power, because of the infrastructure, we are able to do more, and we can do more to really mimic how human thinks about that. Okay, so that's pretty much about the history. 12 words, right? Okay, for that. Okay, so let me quickly introduce our panelist. And the first panelist is Derek Anderson. Want to say hello? Yeah. So Derek, we hired him from Mississippi State. He's great. In terms of AI technology, machine learning, and then application in many areas. He's going to talk more about that. He's an associate professor from Electrical Engineering and Computer Science Department. The next speaker is Grant Scott. Grant Scott is a co-director of our MS degree in Data Science and Analytics program, and also a faculty from Electrical Engineering and Computer Science. And he's leading a large-scale training grant for data science for federal employees, about $12 million, more than that. Yeah, he's going to break up more about that. Okay, Lincoln Sheets. Okay. So I call him Dr. Sheets because he had 2 doctoral degrees here. And one is medical degree, and he decided to go for a PhD degree in informatics for that here. So Dr. Sheets is going to talk more about in healthcare, right? Application of AI in healthcare. And let me introduce Dr. Edward Brent. Dr. Brent is a chair and professor from sociology department. And we chatted a little bit about the winter, the AI, back in 70s, you involved in AI when Don Lindbergh is the National Library of Medicine, was the National Library of Medicine director, was a pathologist here, and went to NIH to lead the entire nation's informatics and some data science initiatives for that. So Dr. Brent has been with those exciting and then sad cycle and exciting cycle here. So without further ado here, let's go for Derek Anderson to talk about AI in drone, right? In those areas. Okay. Yes, please.
Does this work?
Yeah.
All right. So For the next 10 minutes, I'm going to go over from some examples of kind of what we're calling AI nowadays, which Chi-Ren really alluded to. When I started out at first and it was an AI, we were about the third heartbeat. It had died and came back and died and came back, and it keeps dying. And everybody says, don't get a job inside that. If you want to do it, spend your career on it, but go get a real profession. Go do databases, do image processing. So what most people are calling AI nowadays, which kind of strikes a little bit of oddity to us because in the early 40s, one of the first technologies was actually things called neural networks. And so now we're calling AI this deep learning, which is resurrected multiple times. It's a rebranding of neural networks. But as I'll go through today, there's some reasons why we're paying attention to it now when we didn't pay as much attention to it previously. So what I'm going to discuss here today is deep learning for what it's kind of became famous for, a lot of computer vision, so a lot of image processing, and then now it's made its way to audio, to non-traditional sensors. But really the motivation for this is some event happens in the universe. When that event happens, we know about it by light and the transportation of either the reflectance off of that, the emission from that event. And now humans either see or a computer records, but we build an internal picture. And so this is just a field of different responses that has converted light into some electrical response, but yet the brain now goes and does its thing, says, hey, I got Truman out there now, so it tries to do things, find shapes, find edges, find objects. And then the deeper we go in the brain, we start to get these semantic concepts. Truman has celebrating a victory. So it's kind of a process. It's a transformation of data to data, but we put some importance with this data. We call it now information. It's more semantic. It's relevant to all of us. So we're just transforming and transforming and transforming this information as it goes through the human brain. Now, the way that we're nowadays looking at this is we're calling artificial intelligence deep nets. And so as part of the deep nets, we have this architecture where there's multiple layers, hence the deep part of it. And at the very beginning layer, we get something like the image that's brought in, and we get a whole bunch of little tiny pixels. You got a camera, a bunch of individual pixel elements. And now each one of these we can think of as a input that was registered by something like a neuron. It's actually converted electrical light into an electrical impulse. But now as we go deeper through these layers, we build layers of other neurons that take the responses from those neurons, like mimicking the human brain. And we're coming through and we're going to learn little tiny filters or patterns. So at the low levels, it's like the low level human vision, and it's trying to find little shapes and corners and colors and stuff. So we get little tiny responses that the human system's looking for. And as we go deeper and deeper inside this system, so we go more and more layers in, we start to recognize more complex patterns by putting all these pieces together. And so as we start to assemble them, we go from things like, eyes to faces. And as we go deeper and deeper, we move into more where we just say, hey, now logic happens. Reasoning's going on. We've abstracted the signal now to some internal representation, and then magically inference, high-level logic is now happening just deeper down inside the net. So you can tell I have a little bit of irony that I'm throwing inside here. We have a great tool, and it's a great story, but how and why it works is still up to intense debate, and that's something I'm going to talk about today. But what we're using it for now here at Mizzou, two applications of this, of artificial intelligence, which includes deep learning but goes beyond just the deep learning. We're using it to save lives. So soldiers, people that have actually put their life on the line for America, when they're out there, they are now in harm's way. So there's things like explosive hazards that could actually, harm them to worse. And now we are able to build drone technologies that use different sensors and use AI on board for processing to be able to go through and to detect things that they can't see. I'll discuss that. And to discuss things that they should be able to see, but they're so overloaded that they may miss it. So we're trying to save lives, and so now we're using artificial intelligence to go through and to look at different sensing modalities, to look at thermal. So things that are hidden and obstructed, they will create a byproduct, a signature in thermal as they radiate the heat that can actually be seen. So these are things underneath the ground that now we have actually a drone technology for that can go through and detect and find hidden things that otherwise we can't see. So it's a benefit to the person. Other things like three-dimensional radar. Now we can actually send transmissions out into the world. We can penetrate the ground and so forth and actually get depth penetration, and we can see things that are really deep. And now they become 3D volumetric spaces, and now we have AI that looks across 3D, looks across radar, looks across infrared. It also comes through, and we're looking, this is what a picture, if you actually project into the ground, that's something hidden underneath the earth that we're trying to find that would otherwise cause harm or worse to an individual. And so one of my PhD students has spent some time, and it's really hard to get data. So we've also created AI that takes a few examples, and it looks at those few examples, and it tries to dream up new examples that are data that it's never seen before, but it thinks follows those patterns. So now, instead of hundreds of thousands and millions of dollars we're going out and collecting, we can generate our own data that half of these are real data and half of these are the AI created. So if it's good enough to fool the human, it's good enough for us to probably be able to, take and use and improve the AI. We also do a lot inside here for, as Chi-Ren had alluded to, really data and processing power is what's pushed us along in this new era. And so we have a lot of new devices, which this was better than my computer, a little board that's very cheap now, and it's the cost of what the power of what my server was a few years ago. And now we can put these on drones and actually do the AI on board, something I would have laughed at probably 5 years ago and said, yeah, we're not going to be there. But beyond saving human lives, we're also looking on campus right now. We're using this for going across a variety of different platforms, from robots in the field up to satellites. And we're looking across these different sensors and spectra, like I discussed over here. And now when you come to other applications like ecosystems and talking specifically about agriculture, talking about plumes and water quality, and looking at things like invasive species and many topics, we're having a cohort, a group of us that are actually working right now towards trying to take AI to go across all of these sensors, to go across all these platforms, and to be able to detect and find information. But the explainable part, which I'm going to discuss next, is a way for the machine now to relay this information back to people so that it can have a better connection back to the experts to either describe why it's doing it or to help find discoveries which can aid us in trying to answer one of the hardest things about science, asking the questions we don't know how to ask. So this is the point of what I was going to discuss today, was explainable AI. So one of the challenges is you got an artificial intelligence. What did it learn? Grant came in and was sitting in my lab last week, and as he was sitting down here, we had a great Mizzou sticker on the wall on him, and as he just starts playing around, he moves a little bit, objects, start going out of view. We no longer see a chair, but now he puts his hand up here, and all of a sudden it says it's a Frisbee. So a Frisbee, I guess the machine learned it's a shape of something, and it probably has something like a hand around it. So, that was the description. It learned some context probably of a person with hand around an ellipse. But how do we know this? If we just create an AI and we just run it on data, we really don't have a clue what goes on in the mind of the AI. We're kind of stuck to running it and seeing what we get. We also have a lot of things where we come through and can take an image and we can alter it by adding noise to it, and you and I wouldn't see anything different, but now it's going to change completely from thinking it was a panda to a completely different class. So we have no clue what it's looking at, what the features are, why is it doing what it's doing, and that's pretty scary, right? As you got smart cars and you got Alexa sitting inside your house. We can also go through and put things like stickers. We could take an image down here that says, hey, it's a jaybird, but now we come through, put a little sticker inside the image, and it's a toaster. So now you got a smart car, somebody come out on a stop sign, put things like a sticker, and for things that it's looking at, you could completely change its classification. It's not going to find those objects, and obviously it's going to change the behavior of the application, right? So it's a real touchy subject. So we need to get away from black box, and right now the XAI is being held as a third generation, and I think it's a good thing for us to get into is to the explainability. It'll help us design better AI, but it'll also help it integrate better with humans. But the hardest part about this thing is, what's the question? It's saying, what did you learn? Is a very open-ended thing. So it's really hard to come through and to figure out what questions to ask the AI to say, well, what did you learn? Because it doesn't know how to talk to us. And so, there's a lot of us that look at theoretical proofs, and there's a lot of us that look at experiments, running these types of things, like what if I put a sticker, how does it behave? Versus looking at convergence theorems and so forth, or proofs to say, how does it behave? And ultimately, it can help us design better AI, or I think be just responsible at that. So the two examples I was going to give today of explainable AI is, one is there's visual. And so for visual AI, you give it an image, but now we're trying to say, what do you want to get? So you come in here, you give it an image, it gets some features as it goes, and it processes all that deep stuff. And then it has a procedure for coming back and propagating back to the original image the things it thought it saw, and it kind of finds a heat map. From this heat map, we can look back in the original image and say we think it found wheels, we think it found a bar, and that's where we're kind of at now, is we can kind of get some evidence. But what we probably want when you get an image is I want a machine that say, I found a bicycle because I see 2 wheels, a seat, and handlebars. I'm going to feel less certain if it actually came back and said, I found a bicycle because I found a wheel and a banana. The AI is looking at something wrong. And so really here on campus, what we've been using this for is explainable AI for fusion, is we're fusing things all across the electromagnetic spectrum, infrared, radio, visual spectrum, hyperspectral. And so we take all these things, and as we do it, we're doing data fusion, we're combining all this information, but now we're doing explainable AI. As the machine does this, we're trying to say, we're developing techniques and new mathematics to say, hey, how good are the inputs? What's happened in the electromagnetic spectrum? How do things, did we get good training data? You give me a bunch of data, I say, hey, I can't learn anything from this, or, so it has to be able to have a question and then to be able to answer something about this question and our quality to do it. How are the parts interacting with one another? How does electromagnetic and how does ground penetrating radar work together to find buried things? But also, what's missing? That's one of the important parts. If we can find out what the AI doesn't know, we can go back and try to direct new data collections or try to improve the way the AI is doing what it's doing. And then last, how much do we trust those decisions? I like to know if it found a stop sign, I'd like to know how much it believed it was that stop sign, right? Before just taking it at face value. So I think at that, I'll hand it on over to Grant Scott here. Today was going to be an odyssey of listening to 5 different topics. So,
sorry, I looked over anxious there to get that microphone from. Well, luckily Derek covered a lot of the hard stuff about deep learning and stuff like that. So I'm going to actually retouch on this. And so one of the questions that we actually have to look at is deep learning as powerful as the human brain? Because a lot of people are kind of heralding it with this idea that we get these deeper and deeper networks, then we can potentially mimic the human brain. Derek hit on a lot of the things. The stuff that's missing is the reasoning, the understanding of what the networks are doing. So deep learning has really become to dominate things because we've got so much data, so much computational capability that we can actually train very complex things that can do things like natural language processing that you've heard about, image and video processing, object detection, segmentation, medical image diagnosis. These are things that we've encountered in pop culture that you start to see in the headlines. They're the wow things. Your automated suggestions, like what we heard about with Alexa, listening to conversations, and then you go to Amazon and it's, here's everything you were talking about, ready for you to buy from me, that sort of stuff. Or, music playlists and stuff like that. If we think about the human brain, though, if we look at this as kind of pretend it's a machine, it's got thousands of synapses connections on every neuron, billions of neurons, and if we look at that as a whole system, that's over 100 trillion connections. Those are ways of flowing information through from those inputs and detecting, reasoning, etc. All these things that humans do so much better than machines. And so really this is an unparalleled computational ability. We're a long ways from having AI that can get to this, I think. Maybe. Depends on who you ask. But I like some of the examples that Derek showed up, because I know I've seen stop signs with stickers and graffiti on them, and I don't want a driverless car rolling right through a 4-way stop because somebody put a sticker on it, right? So that should scare you. And I tell you what, if you ask people if they trust driverless cars, the people that know more about AI and machine learning are less likely to trust driverless cars. There's a reason for that. So deep learning and all machine learning really is only as powerful as the training data, which is a little bit of what Derek was just saying. You have to figure out what the machine knows, why it's making decisions, why it's deciding to do these things. So deep neural models especially, they've become this dominant machine learning AI with thousands of neurons, millions of connections. Now compare that to the previous slides where we had billions and trillions. So that gives you an idea of how short we are from really getting to the true human brain capacity. These connections in these deep neural models are basically parameters that we tune with data. These are the ways we teach the machine to do the recognition and maybe some reasoning and some agglomeration of concepts like what Derek showed with the 2 wheels and the banana to call it a bike sort of idea. So what it really comes down to is, do we have the data volume and diversity to drive model performance, to drive an AI to really be robust enough? Because what they see and what you saw with some of those examples is if it doesn't have enough diversity of exposure, then the AI it makes bad decisions. If you look at the human brain and how it's learned, it has been training, for me, it seems like a really long time. Maybe I reset once a month. But for most of us, right, our brain as a machine, as a learning machine, has been learning for 10, 20, okay, I was about to go bigger. Lots of years, not quite 100 for any of us, I don't think, but nonstop learning. These models we train for maybe weeks or months, and they're not near as robust. So that's one of the challenges. So as kind of an exercise, what shape do you guys see if you look at this? This is a machine. If you asked it what shape it sees, it would come up with a lot of different answers depending on the data. If I told you as people, do you see this as a diamond or a plus? How many people can actually conceptualize a diamond or a plus from those 4 dots? Everybody. You guys have an ability that machines don't have, because you can create imaginary data to fill in the blanks based on reasoning and knowledge and your prior experience. If a machine tries to recognize something and it doesn't have enough data experience, it just can't do it. So you hear a lot of clicks and they don't always work. There's like some magic range and I keep stepping out of it. So if I add a couple more dots, obviously it's not a diamond or a plus. And so just depending, as I get more data, then I get more information. And this is what a machine needs. So now the machine can say, oh, it's a circle because I've seen enough data to understand that this pattern is going to emerge. It's going to be a circle. And so that's one of the key elements. I'm clicking. There we go. So we go back. I thought Derek was going to give you guys a nice mathematical explanation of this model. So I wasn't planning on covering that. But this is, again, another example of what a deep convolutional neural network, it does detect, assemble, decide. This is kind of what Derek said. So one of the challenges is he talked about the way over here where we've got all these different assemblies and detections and stuff like this, but we don't know really how it does things. We can try and back project and find the hot spots in the image, and we can try and figure out what is the machine doing, but we don't necessarily know. So one of the cool things that we're doing here at MU is working on ways of developing some new neural architectures that actually do parts-based assembly, kind of like human reasoning. So if you look into some of the research about how human vision develops, we recognize components. So when babies, one of the first things they're really good at is recognizing faces, because everybody's sitting there going, oh, it's so cute, like right there, human face right in its face all the time. They pick up the eyes, they pick up the mouth, they pick up the facial expressions. And so machines need to we need to think, how can we design something more explicitly to learn like a human does? So how many people see this image and think that's a dog? Only Derek. But most of us see a duck. What makes us think it's a duck? It's got this goofy beak, the feathers, the wings, this sort of thing. Well, what if we can actually precondition these learning machines like deep neural networks to basically decompose something they're seeing into significant parts and then learn to model parts and then begin to have activations and recognitions that actually are firing on those parts, to get a little bit further to that reasoning so that we can see how is it reasoning. Can we build that reasoning, that parts-based recognition, so that we can trust it? We can interrogate how it does the things with a lot more. And so this is one of the projects that we're working on here at MU. One of the key things that I always try and hit on is even the best machines, especially AI, they always need a friend. They cannot do anything on their own. So deep learning is usually only a part of a solution. Deep learning, AI, it's part of a solution because we're really good at building data-driven models, data-driven AI, machine learning, but those things aren't good at doing all that higher level reasoning, taking in all the things, all the examples, the context that it may not have seen before. And so if I'm building a system like this that can go scan the earth and find interesting things, if you look at this system, the deep neural model, the deep machine learning is only a small little beginning nugget, and I need more advanced things coming in here that puts a human over the loop or a human in the loop or human-machine teaming. This is one of the things that I'm a big proponent of, is that you don't trust AIs to kind of do their thing on their own. You need to have a human when they're doing things that are critical. And so machine-assisted human-machine teaming for assisted human processes can greatly help us. That's one of the areas where AI is most exciting and can get us a lot of kind of value without a lot of potential downside because we keep that person in there. So another area to discuss, we've got one of the other areas that we look at is geospatial machine learning. So the world, we're awash with data and sensors. How many people have a cell phone? It's sitting there collecting the data right now, so Google and Apple can sell you everything you don't actually need, but maybe you want. Geospatial information is a very broad area. Everything has a location. All these points, lines, outlines, pictures. If I show you guys this picture, I've labeled it Colombia, so it's fairly easy for you guys to say, oh, that's Colombia. And if you're looking at it and you've looked at anything from above, you can say, hey, there's an interchange. And knowing that this is Colombia, then I'm going to use some extra information and infer that that's 63 I-70, kind of hot mess of an interchange. I'm trying. There we go. So one of the things we're doing is exploring deep learning vision modules coupled with geospatial information to predict a lot of different things. We do it for object detection, and one of the things that I'm working on with Dr. Sheets, that you'll hear about in a little bit, is going further and trying to let computers help us understand the vision characteristics such as green spaces, sidewalks versus buildings, and other aspects of the environment, and then bring in layers of other information like census data and health data, and then can we begin to understand population health from both space and the ground at the same time. So that's another example. And that's my segue into Lincoln Sheets.
Thanks, Grant. All right, let's see if I can figure out this clicker that my colleagues have mastered. So Grant and I are working on a couple of really exciting applications of satellite data. One of them is to use machine learning on satellite images to predict the obesity rate in a neighborhood. Obesity is a huge problem and going to be a bigger problem all around the world for health, right? The more people are obese in an area, the more cancers and heart attacks there are going to be, the more money we're going to have to spend to save people's lives. If we could predict and prevent obesity, then we could make lives better and save money at the same time. So Grant's looking at satellite images. I'm starting at the other end of the equation. We're going to try to meet in the middle. So these maps aren't actually based on artificial intelligence at all. This is, Grant said, and Derek said, that AI is only as good as your training data, right? We need to know everything we can about where the obesity rates are higher and lower. So these maps of obesity, of rural versus urban obesity, are just based on old-fashioned survey data. Workers went out to villages in these poor countries all around the world and measured people's weight and height and took lots and lots of human-gathered data. Now we're starting to turn that into information about obesity rates. Then Grant is going to take that information and feed it and satellite data into a deep learning algorithm. And we think we're going to start predicting what kinds of things are related to obesity. But, like he said, maybe it's sidewalks, maybe it's green spaces. We have to have some hypotheses. We have to tell the deep learning machine what to look at and start finding which of our hypotheses are true. We can use population level data to look at health a lot of other ways. We can talk about, there's lots of data in Facebook, right? Who here uses Facebook? Or Twitter, right? Or Instagram. Anytime you put a post on Instagram, that says something about who you are, where you are, and maybe something about how you're feeling. There are deep learning algorithms that can read millions and billions of posts and start to say, these people are depressed. I think these people have a 67% chance or a 93% chance of being seriously depressed. So far, we're just collecting that data, but very soon, we'll be having a debate in our society about should we reach out to those people. Those people aren't posting because they're asking for help, or maybe they're asking for help from a friend, but they're not asking for help from the hospital or the government. But the hospital or the government could be watching Instagram and Facebook and reaching out to people and saying, I think you should talk to a counselor. I think you're depressed. I think your risk of suicide is higher than average. We need to do something about that. That starts to get into privacy issues, doesn't it? It's going to talk more about the good and the bad side of AI. But one thing that we need to think, prescriber patterns, we need to talk about pill mills. We need to look at who's prescribing too many opioids in what neighborhoods. One thing we need to think about with AI is if we're teaching AI to be better soldiers, then that's going to have a different outcome for us 100 years from now than if we're teaching AI to be better doctors. When the singularity happens, Ed's going to talk more about the singularity. When the singularity happens and our machine overlords run our lives for the rest of history, we're going to hope that they descended from AI doctors and not from AI killing machines. Those are decisions we have to make now that are going to have repercussions for future generations. This is a partly AI system that I worked on, talking about humans over the loop. We used AI to predict which patients are most likely to come into the hospital in the next 6 months. And it was these 22 experienced, talented nurses whose job it was to watch these 10,000 patients, see the ones that were slipping through the cracks, that weren't being seen by their doctors, and the machine told them, this patient is more likely to need a doctor, to come to the ER in the next 6 months. Their job was to talk to the patient before they showed up in the ER. Say, we need to get you in to see your primary care doctor. Genetics is a big part of big data, a big part of informatics. It's a big application of artificial intelligence. We don't have nearly as much genetic data right now as I think or as you think, but we soon will. We're going to get, who here has had their genome analyzed? Something like 23andMe, or maybe your healthcare system. I haven't either, right? We hear a lot about 23andMe, but very few of us are actually in that database. Those databases are growing exponentially. Things like the Precision Medicine Initiative is getting a lot of funding. And things like the All of Us initiative is working to include more diverse samples of genomes from the entire US population so that we are really looking at the right data. AI is only as good as our training data, right? And very soon, we're going to have way too much data. Chi-Ren and some of his students are doing great work on using large volumes of genetic data, saying these genes belong to people with autism spectrum disorder. These genes belong to family members who don't have autism spectrum disorder. What are the differences? Instead of having a theory, a hypothesis, we can use big data to do data-driven discovery and use AI to find patterns that it would take a human many lifetimes to discover. AI can move faster than that. Let me talk just for a minute about biomarker screening. If we could identify depression from Facebook, we could, or maybe we don't want to, reach out to those patients. What if your toilet were screening your urine for glucose, right? What if your toilet knew there's sugar in your urine? That's the way Hippocrates and Galen, those ancient Greek doctors, that's the way they diagnosed diabetes. They had to taste your urine, and if it's sweet, then they think you've got sugar diabetes. So that might be something that we can choose to have soon in the future. Right now, your Apple Watch can tell you, I think you've got an abnormal heart rhythm. You should talk to your doctor about that. Robotics is a big part of AI. This is a Da Vinci surgeon. This is a robotic surgery. This guy, this surgeon here, is actually operating the tools for laparoscopic, minimally invasive surgery. But this machine is getting smarter so that it can learn some of the simpler parts of what the doctor is doing, and it can do those parts for him. It's kind of like driving a car, right? You use vision to operate a machine. And the human over the loop is going to be essential for this for the foreseeable future. The Da Vinci can't do the surgery by itself, but it can do some of the really minuscule, tedious parts, while the surgeon does the big picture parts. Natural language processing, you don't think of language as being essential to what a doctor does until you sit down in your doctor's office and tell her your symptoms. And she looks up some possibilities and thinks through what needs to be done. This is a system, I'm not going to talk about the details because I need to turn this over to hear what Ed has to say about the big picture. But this is a system for low resource environments, clinicians in poor countries around the world who don't have internet access, to enter a simple question. An artificial intelligence system at the National Library of Medicine in DC is turning those words into answers about what that clinician should do and sending back a very short answer that can be accessed by a text message. So in all these fields of image processing, language processing, and robotics, we're starting to figure out how to make doctors the model of what AI will be in the future instead of soldiers. That's my hope. That's my advice.
Wow. Wow. That's one of those 3 words. I think I'll need a few more than 3 probably, but we'll see. Which one am I doing here? I never used a clicker like this before. I need a machine to tell me how to do it. Okay. There we go. Wow really applies because there's a lot of good stuff in AI, and you can see why it's beginning to have a huge impact throughout our lives, and has for quite some time. But it's a two-edged sword, and there are some negative things too. What I'm going to do is sort of talk about the stages through which AI has evolved, and how at different stages there are different threats or different concerns we need to be aware of. There's a lot of positive impacts, of course, machine learning and all of that, and a lot of promising future claims. That's the good side, right? The other words, like wow, no, there's a lot of risks, and as it evolves, those risks become more apparent. Early on, a lot of the things that happened with AI were that it simply did not work. We tried things, they tried things, and they eventually dropped them. The perceptrons, the predecessors to neural nets, the predecessor to deep learning, didn't work, but they found when they discovered why it didn't work, they were able to go beyond that. So these early failures seem like a bad problem, but they are a path to eventual success. So sometimes the issue is not, can AI do this? And the answer is not no, but not yet. Not yet. There's a tendency for us to oversimplify and to think that AI is only used when it's doing a better job than humans are. But that's not always the case. There's a lot of applications in which it makes sense to use AI before it's perfect, before it's even as good as a lot of people. At the far right here, it would be better than all humans. That's a pretty good sign. That's the time to use it. But there are other reasons why we might want to use it earlier. If things have to be done really fast, or a great deal of volume of data, and humans can't do it well enough. Safety issues. If you're going to be cleaning up a nuclear reactor that's had problems, you don't want to have people in there. You'll settle for a robot that's not as good as a person would be, but we don't care as much if they don't survive. So there are reasons why we might adopt it earlier. Sometimes that's done for poor reasons. If you think about the phone answering systems, they're a lot worse than any human would be, or than most humans would be. Yet they use them all the time because we're stuck going to that company and listening to those machines, trying to figure out when the human should be involved there. You think about all the forms you fill out for lots of things these days online. Now we're doing a lot of the secretarial work that they used to do to create the documentation for things. And so they've transferred that data. They've passed the costs of that out to us. So there's some bad reasons for using AI, and we can use it too soon. One concern is we don't really know quite where this line is that we're drawing here. Has it really achieved that standard? So we may think that it's way over here, better than all humans, but then we have something happen like the 737 MAX, and we realize it wasn't quite as good as we thought it was. Maybe the sampling that trained that wasn't as good as it should be. So we have to be careful, and there will be a lot of mistakes and a lot of errors. And we need to design systems that use humans and machines together to try to protect us against those errors. One other way that AI can be a problem is it can work too well. And that's where it starts to have, it's adopted, it's widely used, it starts to have implications for lots of things. Disruptive technologies that cause job losses. If you're a long-distance trucker and you're looking at automated driving, you're beginning to worry about your future career, and should. And that's a real consequence for them. AI is a lot greater danger to continued employment for most of us than are immigrants, which a lot of people are concerned about these days. And in fact, at the bottom here, political disruption. Our notions of are trying to deal with the fact that AI is taking so many jobs and changing so many jobs, and the fast changes have caused a lot of people to feel pretty worried about life, and that's changed a little bit about how politics has gone. Externalities are where they pass the costs off to other people. Increasing inequality, AI is used primarily, developed and used and available to richer people and to corporations, and it increases the inequality. It's also transforming our lives, so things are not the same anymore in a lot of ways, some good, some bad. The loss of privacy, we've talked about that already. It also changes how people interact. Some studies have shown that if you have people interacting with other people and with computers, if the computer's always right, people lose their incentive for playing the game or whatever, and you get discouraged, understandably. But if they've done studies where they have the computer be wrong sometimes and admit it, and when they do that along with people interacting, the people in that same circle interacting there act a little better too, and they acknowledge when they're wrong, and it sort of models human behavior. Other cases where this happens is where they have like robots to help the elderly or people who need help, and they tend to sort of personalize them and anthropomorphize them and think about them as humans, and they can be that really changes how we relate to machines. It also changes how we think about work, the very nature of work. If we have an area like trucking where we can reduce the number of people who are employed, at some point we're going to still have lots of wealth in our society, maybe more than ever before, but we won't be able to fully employ people in interesting jobs that are challenging. So do we really need to have everybody work? Maybe some of us who are able enough, lucky enough, fortunate enough to be able to have interesting, exciting jobs can keep working and doing things, and other people don't necessarily have to work at those low-level, low-skill jobs that aren't going to help very much. So the notion of a guaranteed income, that sort of thing, begins to be considered when you have AI. That's changing the way we're doing life in a lot of ways. AI can become too important. This is where it's so successful and it's so pervasive, it increases our dependence on it. Think of some of the areas where we depend heavily on AI already. the infrastructure. Think about the power network, power grid. If that gets turned off because of something that happens, some malicious event or something. The stock market, voting, we've seen issues there. The greatest present danger, I think, is malicious use of AI and sabotage, like in the election, bots and fake news, cyber warfare, like Stuxnet, malware, IP theft. The most talked about long-term problem is the singularity. The singularity would be where computers begin to be able to exceed the power of humans and begin to treat us badly. Okay? So at that point, it's no longer that people and machines need to both be in the loop. At that point, machines can do a better job than humans can, and we're out of luck. So that's another concern.
Thanks for all like speakers, like great presentation. So like in the next 30, do we still have 30 minutes to go? Okay. So like I will invite all our like speakers to the front. Like we will have panel discussion, and then let's have like open discussion first, and then if the open discussion like we still have more time, then we'll go into like more topic specific discussion here. So I'd like to ask like the audience about like from the presentations you can see the technology has been here, and then like what would be your most concern about AI? Yes, Dennis. Yeah.
Hello. I'm a university professor, and one of the things I find most troubling, 20 years ago it was easy to advise students on what professions to take and what would be the logical likelihood of happening in their lifetime. But nowadays I really don't know how to advise them, because from what I read, I don't think my job is going to exist 30 years from now or whatever. So my question is, the rich CEO hires an investor guru to come in and talk to him, and he tells him what's going to happen. And the rich guy says, I don't care what's going to happen. I want to know when. All right. So could I get just a year when you think the university might be obsolete?
Oh, I don't think it'll ever be obsolete, but it'll. There's a lot of diversities. Some universities will be obsolete faster than others. There'll be changes in universities. So that's where I'll stop.
I guess on one of the last slides, there was a singularity, right? Until that moment of the singularity arises, which I'm very pessimistic about, we're a little bit more confident in what we can do right now than what we actually can. We still need people at the helm. So a lot of the technologies that we're developing, they're not self-developing themselves, but a lot of the other areas that these are going to be applied to, that is a very serious concern, because now it's not as much of, is this a perfect machine, but can it do better than the human? And if it exceeds or even matches the performance of the human, I think that is a very serious concern for universities and society and, all the alike. So, no, I've been in AI for 20 plus years. I don't have that same level of optimism. I think we have fancy calculators right now that are running better than they ever have. But the point where we're going to have an industry of just an automated, entity without a human in the loop or human over the loop, I don't see that in the short term. I think there's always still going to be a person there, but there may be fewer people. It may be somebody for oversight, not 20 jobs.
So I can't disagree with that. So I'll go with maybe just a more comical answer. I did the math and I retire in 2035. So I think about 2036. We'll be done.
I think you're in the perfect job for the future. I will make no predictions about the future of the university. Universities may be dinosaurs in 15 years, but teachers are going to be, I think Teachers and entrepreneurs are the two fields that I would tell my grandkids to get into. And in my specialty, this is very disloyal. The AMA is going to blacklist me for saying this. But I would tell my grandkids to think about being nurses instead of doctors. We're always going to need the human interaction.
So for, I think traditional instruction, definitely AI will play a role. You can go to online, you can all, and then so could be potentially instructors could be replaced. However, mentorship, research, creativity, I think we still need human to do that here. I still have 18 years before retirement here. So yeah, I don't see that going to happen for that. But some jobs, I definitely my kid is in medical school. I just well, if you just look at the film, just look at the image, probably you find some other specialties for that. Right. Okay, next question.
How do you screen against deliberately false or sloppy information when you're building these systems?
Go ahead. I think they can do that. Yeah.
That is a really hard problem. That is the most exceptionally hard problem. I've done a lot of work with benchmark data sets and kind of using those as a basis of comparison of models. And when I dig down and try and figure out, I've got this model nearly perfect, why doesn't it work? Why doesn't it not get perfect? I found that the data provided was wrong. It was just categorically wrong. And I'm like, okay, great, this is this benchmark data set and it's created wrong. And I don't think we'll ever be able to overcome that issue in the data itself, because as the models get more complex, you need more and more data, which makes it less and less tractable to weed out all the bad stuff. And so what you need to do is develop more robust systems that are more flexible against bad data. I think that's kind of the way that will evolve. Good luck.
So data quality, whatever makes it to the data definitely makes it into the AI. And so now the word you keep hearing is biases. They keep propagating in, and with the more that they're black boxes, these biases that make it into the data itself are going to just become a part of the model. So I think us knowing a little bit more about how it operates and to be able to explain those decisions can help us to find out if some of these conclusions may be coming from poor data. But we really are ill-equipped in some sense right now to have this, because the only way they go out is if they're almost statistical outliers, if there's a small amount of bad data. But if we're overwhelmed with having a large portion of misleading data, it won't just make it into the AI, it'll drive the AI. So I think it's a very serious concern, but I think it's not maybe a task you want to leave to the machine. I think the human and our responsibility and obligation now resides with that data to train these machines. They're a child. We're the ones feeding them this information.
Okay, so next question.
My question's a little bit more simple, because I think the singularity happens whenever machines have enough context to have self-preservation like we all do. And once that happens, they're either going to be our friend or our enemy, one of the two. But to me, since I'm a sort of a technical person in private practice, I have a different viewpoint. It's like a day-to-day productivity for me. And I find myself fighting the link between human and machine. That's the hard part, right? I'm trying to code language to try to make my life better and tweak things. And, I used to think that it was capacity that was the big problem, like point data, 3D point data. These models are so huge, how to transfer them. The speed of light's a problem, all these things, latency. But now I realize it's the human to machine link. And think about if you're Siri, and why will, and I hate to be a pessimist too, and I want to hear your viewpoint on this, because everyone thinks the machines are going to take over the world. Well, Siri can't even get my voice to text right now. And the reason why is because it's like us with our eyes closed, and all we can do is hear things. We can't smell, we can't touch. We have no learning, no nothing, and we expect this machine to have context. How do we get the man-machine link without taking your photo algorithm, smelling algorithm, touching algorithm, all this stuff? And that just seems so far in the future that you guys tell me, but how in the hell is that going to happen in 14 generations from now?
I think actually each of us may add a quick comment to that. We think, yeah, that's why I'm so cynical. It's because we act as if we're at the dawn of the era, but really we just have really sophisticated tools at the moment. But now doing these very holistic things like you just discussed, that's another step. And we're really not at that point yet where we have a theoretical breakthrough that's going to take us to that next leap. So I think that as part of this process, being able to go through now and to treat this as kind of the dawn, if this is the beginning of it, even if we're not there, we have a responsibility now to start to ask questions about what happens when we give too much control. What are the possible problems that can be encountered? And I think that this is the time to ask those questions about making sure that as we get it right, we get it right responsibly. So
Can I interrupt? I got MU Information Institute marks for good questions.
Oh, yes. Stem?
That's a tough question. I think that the machine-human interface is really crucial. If you think about the example of the 737's failure, obviously there, if it had a better machine-human interface where the humans could have known what was going on and could have intervened effectively, that would have made a huge difference. And so we really need to build, in terms of best practices, we got to be building these programs, these computers, in such a way that there's a way that we can help them, that together we'll have a hybrid system that's better than either humans alone or the machine alone.
Yeah, I really like that question. I think one of the good, interesting things to look at is you use Siri, for example, and it's that lack of multi-context that hinders the machines. And one of the big shortcomings in natural language processing is the ability to properly interpret sarcasm, which is pretty much how I spend most of my days communicating, at least to my kids, right?
And colleagues.
There's a reason for that. So that's exactly because the facial and tonal cues that go into sarcasm don't get picked up in most natural language processing. So that's kind of a fun one. Ish.
I think as a species, we're kind of at the point where you have little kids, right? And they don't know what to do, and you have to teach them. You can't use that word outside the house, right? That's a word that grown-ups get to use. You don't get to use that until you're a grown-up. And you think, I mean, when you have little kids, it's hard to imagine that they're ever going to be grown-ups. And all of a sudden, they're 16 and they're acting like grown-ups, and you don't think they're ready. I think it's going to come on us really fast when it happens. And I think at that point, thinking about the singularity, which I think about a lot, at that point, how they act as teenagers and how those machines or that intelligence takes care of us in our old age when it's more powerful and we're less powerful depends on how we raised it as a little kid. That's where we are now. It's not exactly what you're asking, but I think everything that you asked relates to how are we going to build this machine to understand its world and to understand its relationship to us.
So I like to use IA instead of AI. It's called intelligence augmentation to human. I still believe there's no way as a human being this species perfect design. We don't learn from hundreds of millions of the samples. We learn by ourselves over time to to recognize things, to make reasoning, those type of stuff here. So still, to me, it's still a far cry from the real human, what human can do on the machine for that here. So I'm sure yeah, we agree for that here. Okay, I still have four more marks here. So good questions.
So my question is kind of similar to his, I guess. Humans have, compensatory systems, so we can compensate for whatever. If something goes wrong, we can still function. Do we have algorithms in AI that are maybe helping to rebuild things that are falling, short, or to, like a feedback loop to help out when it's not performing at optimum levels? And then if this continues to grow, will we be reaching like that singularity? And if we do reach that singularity, can we stop before we cross the event horizon and we are going to get sucked in, like
Hey, I can start. So that's actually a great question, because one of the things that we see in data-driven machine learning models is the concept of data drift, because data is always getting better, and so that's actually changing the characteristics that the machines learn from. So if your data gets higher fidelity, more precise, it changes the characteristics of that data, and you have to monitor those models. And so there are various different approaches, like active learning, continual refinement of the models, and continual evaluation mechanisms, the human over the loop, the quality assurance. Some of those things have to be built into systems that use AI, for sure.
So the reason I'm so cynical at AI is, 20 years ago, we weren't talking the data-driven. We didn't have the data. We didn't have the machines. So we were more still, and even back in the early 50s, Marvin Minsky, Sir Patrick Henry Winston, a lot of others, it was almost more philosophy, psychology. There's a lot of ideas coming in and making a cultivating, we didn't, it was exploration. We didn't know what we were going to be able to create. We created very brittle systems. But now I think the big reason why I don't call these things like deep learning AI is because they don't really have this general purpose, learning. They don't have the ability to say, how do I even formulate what the question is? Now, getting the question is one of the hardest parts. And if I can get the question, maybe I can find a pathway to getting that question. But we don't have general thinking machines. And I think that that's one of the reasons why we're not at that level yet of thinking, bots with singularity and so forth. We just have really fancy calculators. But that's a great accomplishment.
So this X,
So one thing I can see as an issue with AI is the automation of I guess the newly automated and I guess optimized systems like automated cars causing inequality inequality by either allowing the systems to be manipulated in some way or just the systematic inequality arising from those previously uncontrolled systems. And I was wondering if there were any other contexts where you saw this, where you could see this happening.
That's a great question. Teslas are expensive, right? I'm not going to get a Tesla in my foreseeable future, and I'm going to have to spend a little more time and energy driving myself to work, which puts me at a disadvantage to someone who already has the advantage of being able to have enough money to afford a Tesla. The same is true in, I think about this in terms of healthcare, right? We worry about healthcare inequality in the United States. If we look at healthcare inequality between the United States and low-income countries, places like Burundi, it dwarfs the income inequality in the United States. And how we use these resources as university researchers, we tend to think that we're doing this for the good of all humankind. And that's true. I think there's a lot of truth to that. But as entrepreneurs or as developers of new technologies that will be commercialized, entrepreneurialism isn't necessarily about helping the poorest. It's about selling to the richest. And we already, long before AI, but multiplied by the potential of AI, we have this question of, is this going to help the people that need help the most or help the people that already have the most help?
So along that lines, I would recommend a book for you guys. It's called Weapons of Math Destruction. Really good book on the use of data and machine learning models and AI and some of the downsides that have happened in society, kind of directly addressing that question. So it's a real good read.
A great professor response saying, go read a book.
It's a good book. I think the inherent nature of how we interact with each other and how computers are going to fit into all of this is going to tend to lead towards greater inequality. And I think if we want to not just have greater inequality, we need to have some kinds of procedures, some kinds of practices that help us to design machines that don't do that and apply them in ways that moderate that or mitigate the inequality.
Okay, we'll take the final or okay?
Yeah. You talk about, AI as a threat. It seems like what it's really a threat mostly to, if it's a threat, is to the technical, the scientific, the procedural types of things. If it can actually do these things, could it be seen as more of an opportunity for humans to become what is truly human? And that if you've got something like that, that all of a sudden you can have a boom in the humanities, in the arts, things like that, things that don't necessarily require our logical brain, but allow us to humanly be what is human. I mean, to emotionally be what is human.
Yeah, I agree. I think if you think about the singularity, the only reason why we're using a negative context here is we're talking about preservation of the human species. But beyond that topic, yeah, there's a lot of great that it possibly can do. Insights to ourself, bettering for things of the universe, many things. But in this sense, I think that now this is the obligation we have, is we might be on that dawn. So it's I'll pass over here, but I think we've already turned that corner. I don't think we can slow it down. We're already on that high-speed train.
I like that perspective. I mean, just what you said. If AI can give us more time to do the human stuff, the fun stuff, the creative stuff, that'd be a good thing.
I agree. I think it's inevitable that our children will grow up to take care of us in our old age. I think that's inevitable in a species context, and how we train them as kids is going to be what kind of caretakers they are as adults. And I love your vision that this could be the best thing that ever happened to the human species. There's a poem from the 1950s, long before anybody was thinking about AI, a poem by a beatnik poet named Lawrence Ferlinghetti, and it's called All Watched Over by Machines of Loving Grace. It's a vision of the new Garden of Eden where humans are taken care of by these machines that their purpose in life is to fulfill our purpose in life. I can see that as one possible future.
I think the final, yeah.
This is for the man in black there. You had, on your slide, you had put the term deep fake. What does that mean, please?
Yeah, deepfake has to do with this problem of, like the picture that Derek showed, where the machine thinks it's a panda, you enter some noise, it still looks like a panda to me, but it fools the AI into thinking it's a gibbon. That's just kind of a technical exercise, but if somebody does that to a picture of your lungs, and it shows that there's no spot on your lung where there actually is, or it shows that there is a spot, or it shows that every chest x-ray in an entire hospital has spots where there aren't spots and it can't be trusted. These are deep fakes. These are using AI to fool humans. And it can be used for ransomware. Right now, it's being used sometimes to create fraudulent claims, and we're using counter AI to detect fraudulent claims. It's an arms race between fake information and fake detection.
So for image, like deep fake, you can train different types of the image, and then just like superimpose those images into the some original images that can come up with some different purposes for that. And yeah, work on moon. Yeah, that's right. You didn't. And then like another deep fake could be machine learning algorithms to come up with fake news. Fake news, you look at journalists, they can write their own opinion. However, you can put little bit, tweak little bit facts there, and then machine learning algorithm should be able to help to make it happen like this way here, right? So that's the deep fake idea. Okay.
My question is much more narrowly focused than many of these have been, and I don't know your name, but you talked about explainable AI.
Last question.
Okay. It's my understanding that algorithmic AI algorithmic processing is very easy to make explainable, but that neural networks are hard to make explainable. And my question is, first of all, is all AI nowadays using neural networks, and is there only one major type of neural network, or are there a variety of types?
Great question. No, neural nets make up a very small percentage of AI techniques. My field itself is a field of, we have neural nets, evolutionary computation, fuzzy sets. I was brought up in an era of first order predicate calculus, search spaces. We have hundreds of different techniques. Personally, I think in the past, we've done a lot of AI that was naturally explanatory because we were designing the technology. So part of the explanation went inherent with the process that we followed. But now, because of people like myself as well, we've transitioned AI over to more of a branch of mathematics. And as that mathematics, we're identifying functions that can do things like fitting data and converting data into decisions. And as part of that, selling our soul to the study of functions, there's a lot of things they can do, and we've handed over the steering wheel here to to get the performance gain that we have at the risk of not being able to know how the components work. So neural nets are just one thing. Random forests, support vector machines, a number of technologies we can't really necessarily explain. So explainability, lack of, does not just fit with neural nets. It's not only their problem, but since they're right out in front right now, they're a great one just to throw a dart at, you know. But yeah, we have a lot of explanatory stuff right now.
Okay, so what do you think?
All right, everybody, thanks for coming. Thanks for staying. And thanks to the panel. See y'all next semester.